modular invariant. So some new results about them. So I'll start with all the things. So the setup is this. K is a field, and V is some finite dimensional vector space over K, and G is a finite group acting K linear on V. So in other words, G, we can, for all purposes of this, is a finite subgroup of G. And this action automatically translates to an action on the dual space. Therefore, G acts. On the dual space. And this extends. So we can think of, so consider the symmetric algebra on V dual. This is a polynomial ring on over K. And so let's call this thing S. And dimension of S, the full dimension of S is the same thing as the rank of the vector space V, or V is finite, V or V dual. Okay. Okay, so this acts, so therefore G acts on S as graded, meaning degree preserving, K algebra automorphisms of S. In fact, I mean, you can ignore all of this discussion and just, for all our reasons, we can just think of it as follows. Okay, so for specifically, for more specifically, okay, so let us say n is equal to dimension of the rank of V as a vector space. Okay, so let's say, and then S is the polynomial ring in n variables. And what all of this just says is that for all G in G, this collection from Gx1 through Gxn. So these are homogeneous because degree preserving. These will also be homogeneous. Linear things is a basis of the linear forms. Yes, this is homogeneous polynomials degree 1. I mean, which is really the V dual discussion. So this is all that we, I mean, concretely, this is all that we have done. Okay. So this is the setup, and now let's go. Okay, yeah. Okay, yeah. Okay. So what is an invariant definition? An element F inside S is G invariant if G F is for G. This is okay. And the invariant subring, which is denoted by S, the superscript G, is all the F in S. Is that F is G. And it's not very difficult to check that SG is a K subalgebra. Oh, yes. And it is finitely generated. It's an Ethereum. Okay, so this is the setup, and it is this ring that we want to do. Okay. This is all very old. This is all goes back to Gilbert. This is the object that we want. Okay. So now, again, still classical words about polynomial space. So the question is, when would SG be a polynomial? Yes, that is what that was. So this is again theorem. This is also so I'll make all statements here. Shepherd, Dawn. So I should say that I don't know if the way I have understood this statement one is not what they, but it is anyway part. Maybe others. If SG is a polynomial, then G is generated by what is called pseudo reflection, which I will define in a minute. And two is, I know of this is proved by Shepherd and Todd first, and then Chevalier, and then generalizing or changing the proof at the stage. Okay, is that so converse holds. If the order of the group is invertible in K, is a case of field, so it just means the non-zero element of K. It is an integer and its class P. The characteristic of K doesn't divide the order. Okay, so that is okay. So this is what. So just we need to define what pseudo reflections mean. An element G not equal to identity is called a pseudo reflection. If it fixes an if G it fixes a codimension one subspace, E in V is that GB equals V has codimension 1. Okay, so this is how is suddenly gone? It's okay. It's okay. Okay. It's go ahead. Yeah. So this is, these are the vectors V. These are the vectors V that are fixed by this given element, okay, and that has codimension 1. So that's a non-identity element. It's called a pseudo reflection. Okay. So of course, this is something that is not intrinsic to the group, but it depends on the representation. And so the first theorem is that if G is generated by zero reflections for that representation, then SG is a polynomial ring, and converse holds if this is the case. So this, we will look at this condition. Okay, so let's look at an example, which so G, in our case, we just take Z mod 2Z acts on CXY. So I'm just, we can write it as some two-dimensional vector space over C and then take the dual action, etc. But instead, let's just take this way. Right? I want to consider two different ways. So I'll write this as generated by one bar. So one bar sends X to minus X. So this is one action. And one bar sends Y to minus Y. And the invariant ring. So it is easy to check that none of the linear forms are fixed. Right? Okay. One bar will not fix any linear form. It will fix squares and the product. And so then it's not easy. It's not difficult to verify that SG is the subalgebra generated by the degree 2 polynomials. Okay. And this is not a polynomial. There is a relation, there is an algebraic relation among those generators. We can take another representation. So in which one bar takes X to Y and takes Y to X. And then X plus Y is fixed, and so is a product. And then one can put it. And this is a problem. So one can use the fact that X is fixed can be converted to observe that this element one bar is a pseudo reflection in this group for this representation, and that's all. And its group is generated by one bar. So for this representation, G is generated by pseudo reflection, and for this one it is not, and that we see here. So that is the that's the that. So now, so this is just about the definition of pseudo reflections. Next, let's look at the statement 2, where there's an extra hypothesis that the order of the group is invertible in the field. It's always true if K is characteristic 0. Otherwise, it says characteristic field doesn't divide. So, so this is about the statement, which is if it is generated by pseudo reflections, then the invariant ring is a polynomial ring. Originally proved by Shepard and Todd using their classification of pseudo reflection groups, then by Chevalier using other methods, and then by Sayre. So the first things for over reals and complex numbers, first two, and Sayre in general using homological techniques. And the key, one of the key ingredients of that statement, and this is used. I should just say one. Is that if G is invertible in K, then we have an SG linear map called the Reynolds operator from S to SG. It sends a polynomial f to the average over its orbit, which is GF, sum over this thing and divide by all. So this is a linear map, and this is surjective. This map, if you take any element inside SG to just map identity. Okay. So in other words, this inclusion SG. So in other words, there exists a map. There exists a map sigma from sigma as an SG linear map from S to SG, such that this inclusion from SG to S and this sigma to SG is, this composite is identity on SG. So this inclusion map of SG inside S splits. Okay, this is what. Okay. So this we often say that SG. So we say that SG is a direct summand of S when this happens. Okay. So this is an automatic condition when you are in characteristic 0, or in general. This is invertible. When you can divide by this integer in the field, this is automatically satisfied. Okay. So, and this is used in the proof of this condition that invariance for groups generated by zero reflections are polynomial rings. Okay, so now what could one hope? Now we want to come to the modular case. Modular. So now so the fixed notation P is the characteristic of K, and that must be positive because P has to divide the order of group, and P divides the order of group. Okay. So again, this is again a little general because there could be this is divisible by P, but need not be a power of P. But then again, you can split the problem into two steps. So the key, in this situation, we need to understand understand this in the SG when G is a P group. The order of G is the power of P. Otherwise, if there is a G order of G is not a power of P, then we can, but still divisible by P, then we can do something. So eventually, the problem will come down to this situation. Okay, so G matrix is a power. So this is the situation that we would like to understand. So therefore, having set up all these things like this, one may wonder the following. So okay, so now, for now, so this is the hypothesis now. Okay, K is the P is the characteristic of K, and G is a P group. And G is a P group. Suppose that SG. So maybe I should introduce a notation. I will write SG with a vertical bar. This comes to denote. SG is a direct summand of S. I will denote it like this. Suppose that SG is a direct summand of S, and that G is generated by zero reflection. Because that was a necessary condition. That statement was characteristic free. There is a characteristic zero proof which uses Molien's formula, so that is definitely characteristic zero. But using ramification, it's also proved without reference to characteristic. Okay, so the statement one that I had made in the previous board, which is that this is necessary, is quite clear. So G is generated by zero reflections. Is SG a polynomial? So it is natural. I mean, having set up all these things, it's sort of natural to wonder that. Yeah. So the key point is that this is not always guaranteed when we are in the modular case. It may not be a direct summand. Okay? But assuming that it is a direct summand and that G is generated by zero reflections, which anyway is a necessary condition, okay, would the invariant ring be a polynomial? So it is. Okay, so, but it turns out that the hypothesis is. There's some redundancy. So, okay, I should clarify that I am not describing the problem historically sequence, but I just, at least the way I present now. You're not saying again. No, you mean this condition here? But no, it is necessary because if SG is a polynomial ring, then S is also a polynomial ring. Then by outside of Bookstone form, and these are the same dimension. I mean, S is a finite extension of SG. Therefore, by outside of, it will be a direct. Yeah. 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 And take the transformation x goes to x plus y and y becomes y. Yeah. The invariant will be y and the product is. Yeah. Yeah, and that is the invariant. So it's a polynomial. No, I will come. This is zero reflection. It fixes y. The other one is not fixed. No, zero reflection's definition was it as a correlation on fixed subspace. It was not saying what is it. Okay, what happened? Yeah. So I am coming to that in a minute. Yes. Okay. Yeah. So. Yeah. So it appears that it's not. There is a redundancy here, and that is a theorem Rower who was studying this conjecture. So with the hypothesis as in that question, so it could be characteristic of K is P. G is a P group. If SG is a direct summand of S, then G is generated by zero reflections. Which that are not diagonalizable. So they have zero reflections. It is just that they are not diagonalizable and they don't exist in characteristic zero. Okay, so these things exist only in characteristic P, and such things are called transvections. Okay, and they exist only. I mean, every zero reflection is diagonalizable force. Actually, or the field is in characteristics. So, so coming back to this question, then Okay, so then the question is, if SG is a direct summand of S, is SG a polynomial, right? So that is, yes, and that was, so I wrote that as a question, but the precise statement was conjecture. So I'll write that as a conjecture. I mean, just conjecture. So it was originally conjectured by Schrank and Below. And then Bro was studying this. So it was conjectured in a slightly different way, not the way it is written now. We're not referring to direct summands, etc. And Bro, when studying this conjecture, made various observations, and so he sort of reformulated it as follows. Okay, so same hypothesis. Characteristic of K is P greater than 0. G is a P group. If SG is a direct summand of S, then SG is a polynomial. Okay. So this was so the way it is stated like this, it is a formulation of Rover. Okay. But it takes some some work to look at the original formulation and then translate it into this idea that this is a direct summand. Okay, so this is what our results. I mean, not exactly. Our results are about this. So there is another variation of this question, which is designed to solve this problem. So I will make the definition. I mean, I want to state a theorem of Hilbert, and then make a definition, and then that is when our theorems are sort of, I mean, are related to that concept and not exactly answering this directly. So how would we prove that SG is a polynomial? One approach is to use the following theorem. I mean, with this hypothesis, how will we prove that this is a polynomial? So one way to use this hypothesis, it goes back to Hilbert. And it works in general with, without any of these assumptions. So this is no assumptions on characteristic of K or order of G. So infinite group is there. Just only that there is a finite. Suppose that, assume that the invariant ring is a direct summand of the polynomial. Okay. Just assume this. Don't need to assume this part, first time. Okay. Let R1, R2 up to some Rn be homogeneous elements of SG of positive degree. Such that we look at the ideal generated by the positive degree homogeneous elements inside us, such that so we look at the positive degree part of SG, look at the ideal it generates inside us. These are, so this is a finitely generated ideal because it's inside S. Let us say that this is so pick finitely many homogeneous invariants that would generate the ideal generated by SG plus inside S. Then, so this is the assumption. Then the invariant ring is generated as a K algebra by these elements. Just as a K. In fact, that is how in the non-modular case, meaning order of G is divisible, is invertible in K. In that case, this is an easy proof that invariant ring is a Nigerian ring. Okay, because by Hilbert basis theorem, this is Hilbert basis theorem. There is such a finite collection, and therefore this is. So this ideal is what we would like to study. So it is called Hilbert ideal. This ideal generated by the positive degree invariance, homogeneous invariance inside. So definition. The Hilbert ideal this is, of course, it is yes, H. So we need to keep track of G, and also we need to keep track of for the polynomial. This is the ideal generated by the positive degree terms, positive degree homogeneous invariance science. Okay. It's a homogeneous ideal of S. Okay. So this is what is called the Hilbert ideal. And so what the saying is that they compute the Hilbert ideal and look at the minimal generation set. And if SG is a direct amount of S, that's enough to generate this one. So then, of course, we can ask anyway, this is given to us that SG is SG a direct amount of S. That's given to us. So then, in order for this to be a polynomial ring, it would be necessary and sufficient that HGS is generated by n elements, and n is the dimension of S or rank of P. So let me write that here. So that is the question that we answer in parts. So I just want to rewrite this conjecture of Shang. Just to summarize what we discussed at the end, okay. Suppose that SG is a direct amount of this. Then SG is a polynomial. If and only if the Hilbert ideal can be generated by n elements, where n is the dimension. Generated as an S ideal by n homogeneous elements of SG plus of positive degree, where what is n? Where n is the rank of B as a K vector space, which is also equal to the full dimension of S. Because that generating set is what we want, because SG will also be generated by n elements. Okay. So in other words, we are saying that is only HGS. So this will have height n, because the only ideal lying over this inside S would be the maximal ideal, and then going up and down, going up, going down, and so on. It can only is the complete section. So this is the reformulation of the conjecture. I mean, one way, I should not say reformulation, one way to try to solve this, to determine whether under this hypothesis that, this is, here I am back to the conjecture. So this is G is a P group and P is the characteristic. Whatever I stated about Hilbert ideal and Hilbert's theorems in general, Okay, but now, back in the context of the conjecture, the question would be: is this a complete intersection? Okay. This is what we okay. In our results, some of them are just this, and there is another result which is not exactly answering this, but that's what I would like to. So I will. So the answer is no. I mean, answer is no in some cases. So in some cases. For example, if G is abelian, this was proved by Pro. This thing will be a complete distinction. But yes, one should, even in this case, there are situations where SG is not a direct summand of S. All that one knows is that HGS, the Hilbert ideal, will be a complete intersection. But of course, SG is not a polynomial ring, precisely because SG is not a direct summand of S. Okay. So that is there. I mean, it is a genuine. I mean, this is a necessary hypothesis that there are situations in which SG is not a direct summand, but this is a complete intersection. But putting them together, yeah, we would still not get that SG is a polynomial. So that's okay. So this is so now I want to describe our results and I mean so I'll prove. I mean, I sketch the proof of one of it, but I'll list 3 results in this direction. So arbitrary, I mean, N. Okay, so for now, hereafter, okay, only the first. So this is no restriction on dimension. If G is a generalized Nakajima, I will say where this comes from. And this was a class of groups that we defined in that paper, but I'll say that then which is this is complete. I will abbreviate complete intersections. Yeah. Can you give some example of this? No, not. I can say not that I can describe right now, because it has to do with so yeah. So I mean, where does this terminology come from? So Nakajima had characterized all finite subgroups of GLP when K is FP. This is very classical result. I mean, classical, maybe 70s or 80s. Characterized finite subgroups of G of GL and FP such that FP x1 to xn G is a polynomial. So this is so what so that actually requires some definition, some ordering of the basis and some certain shape for the basis, etc. And we are just generalizing that sort of description of it. So it's not that easy to define what these things mean, okay, but also and there are examples, and this is there are groups that are not Nakajima groups, which are generalized. This is a strictly bigger class. This is okay, so the definition and the terminology is motivated by this. So that's yeah. So, yeah, so that's it's a slightly involved definition. So theorem 2 is easy to state and sketch a proof, so I will do that. That
Just one question.
Yeah.
Is G the direct summand of it?
No. There are SG which is not a direct summand, but it is still like but ideal is a complete decision.
Okay. So yeah, it's just that.
No, the conjecture will be if SG is a direct summand, then
Then the one
yes, but
in
S,
this case,
no,
for general
okay,
stuff,
for example, if the upper triangle or triangle, I will check. I do not remember Nakajima's definition. I don't go through.
and delivery are not triangle.
Yeah, no, they're definitely not diagonalized both, but specifically whether upper triangle is Nakajima or not, I think. Yeah, sorry.
Yeah. In this case, that also is not.
No, SG need not be direct summand of this. But irrespective of that fact, the Hilbert ideal is a complete decision. So theorem 2, this is the easiest one to state. So I will sketch a proof. If rank of B is at most 3, 2 is actually not very difficult. 3 is the new observation. This is over K. This is arbitrary K. This is also over arbitrary K of positive characters. Nakajima's result itself is about a rank of is at most 3, then the Hilbert ideal is a complete decision. Okay. I mean, 3 is the interest, 2 is. And then we have a result for dimension 4, which is not exactly about the Hilbert ideal, but it is back to the actual conjecture. So, it will take that again. Some definition that we made, which so the statement is this. So now we're going to assume that K is n, and rank of B over K is 4. Then there exists a filtration. So assume that G is generated by transactions, which is anyway a necessary condition for SG to split out of S. So this is necessary for SG to split out of S. Then there exists a filtration of G. Finite filtration. So it is GI. Such that for each I, GI is generated by zero by transactions. And so now we can consider, so there is S, which is invariant ring. There is S here, which is an invariant ring for the trivial subgroup. Then there is G1. There's transactions. And GI plus 1 mod GI is isomorphic to Z mod PZ, generated by the image of a transaction. Okay. And so then we have subrings S and SG1, inside that SG2, inside that SG3, and so on, eventually coming down to SG. In that filtration, if it is not a polynomial ring at any stage, then it is not a polynomial ring at further stages. Okay. So this is section such that there is, and if SGI is not a polynomial ring, then SGJ is not a polynomial ring for all j greater than. So, I mean, technically, what we should aim to prove is that if SGI is not a direct summand of S, then SGJ is not a direct summand of S. Okay, that is what we should aim to prove. But what we proved is only that if the polynomial property of polynomial ring fails at some stage of the fixation, it will fail thereafter. So this is so. I mean, even getting to the statement of the theorem and what explaining what this fixation is and why is this true, it's sort of calculations. So I am not going to say anything about this. So I will briefly say what is behind the proof of theorem. Maybe oh, I see. Bottom part is
Yeah.
huh? Is it sorry, I was not watching that. Yes. Yeah, so the last line is that there is a filtration, and if at some point it's not a polynomial, SGI, then further down the filtration, it is not a polynomial. That's all. Okay. And as I said, the theorem that we should aim to prove is that if SGI is not a direct summand, then SGJ is not a direct. Okay, so I will sketch proof for theorem. So one dimension. So let W be a subspace of the PG, the invariant subspace of. So let W. This is always we are modular. I mean, we are P group, so this is always non-zero. Let W be a subspace of it. Okay. So define the Hilbert ideal with respect to W, or let it become. Define HGSW, the S ideal generated by the invariants that are inside. So this just means invariants in which invariant polynomials in which summation. Sorry, that's why I don't want W. Okay. So just as an aside, W is inside B. I mean, it's inside BG. Inside. Okay. And then what we mean by W per? So this is the dual of B mod W. And this is inside B star. B dual. And so in other words, we should properly arrange the variables, etc. So S is some polynomial ring in some n variables, and W per would be like the span of the first some R variables. I mean, this is after choosing coordinates properly. Insuitable coordinates. That's roughly what. So what it is saying is that, so in this situation, yeah, so HG SW is W per S. So it's the ideal generated by the first R variables. Okay. Intersect SG. In other words, invariant polynomials in which every term is divisible by one of these variables. So it's in the ideal generated by S1. Invariant forms which are in the S ideal generated by these things. No. No, the complement. R is the dimension of W per. And the ideal generated by this inside. So this is a sub ideal of HD, and so there is a theorem It goes back to Nakajima, like used by Brower in his when he was proving the abelian thing. If H, I'll just write over. If HGSW is a complete intersection, then HGS. This is what Grover used, I mean, sort of inductively when he was proving the theorem for abelian groups. Okay. So this is what. Okay. So then, this is in general now. I mean, arbitrary dimension, not. Although we are proving this for dimension 3, the statement that will make here is in general. HGSW is okay, so we can the W perp is the first from R variables, which is the rank of W perp. Now let us define R to be the symmetric algebra of W perp, which is just K x1 to xr. Okay. So this one is actually extended from this. That's the key observation. That this this ideal, which is related to this and this property, the ideal generated by invariant satisfying this property, is actually extended from this smaller ring. So this is, I'm not going to prove this, but remark. Okay, so G acts on R also. That's, I mean, that's what I meant by suitable coordinates. Okay. I mean, there is a way of ordering the coordinates so that the first R variables are, first whatever number of variables is G stable under for this G action. I mean, in other words, G is some sort of triangular action. Okay, so G acts on R. So this statement is subsumed in this thing that insuitable coordinates. Okay, so there is an HGR, and we can. I mean, what? In fact, one of the natural ways to prove this would be to prove that this is equal to this. Then by induction, this is a complete intersection. Therefore, this is a complete intersection. Therefore, like complete. That's what we could have tried to prove, but that unfortunately is not true. This is not equal to. In general, there are situations where it is true. Okay, so this is just the remark is just to say that this is not the Hilbert ideal for the action of G on R. In general, this is bigger. I mean, of course, this is inside here. In general, HGSW contracted to R is bigger than HGR. So, I mean, if it were equal in general, if it were equal, then we could have just moved this by induction, but it's not equal. That's why we're only restricted to some. We have to do some trick which will work only in small dimensions. Okay, so it's now I'm restricted to dimension 3. Or yeah, I mean, the next lemma that I'm going to state is probably not very useful in higher dimensions. Here is. So this W, for every W inside VG, this is defined. But if rank of VG is at least the rank of V minus 2. So this is a somewhat very special case. In general, one would not expect that a large dimensional subspace is fixed by the group. Okay. Most actually that will not happen. Then H G S VG is a complete decision. That is sorry. So maybe I don't want to sketch, but the basic idea is that every ideal, I mean, is that x1 is inside each G R G S G, and this is extended from which is extended from kx1, x2. But any ideal extended with this property will be complete because you need only one more generator, which should have some x2, I mean, some power of x. I mean, the final step is just some observations like this. Okay. But then if you put all these things together, this gets theorem 2, which is that if rank of V is at most 3, then rank of VG is at least rank of V minus 2. If this number is, I mean, right hand side is 1. Okay. And that is the so this is observation, and then with this condition, one gets this is a complete section. Then one does this. That's the sketch of the proof of theorem. Others are, as I said, either the definitions or the proofs or both are somewhat technical and a lot of calculations. I will not say. I'll stop here.
Any question?
Oh, actually, that is equivalent to SG being SG. Correct. Is it equivalent to SG being flat? It is equivalent to SG being a polynomial. So that is Sayre's proof for the in the non-modular case. Yeah. That splitting will imply flat, which will imply projective and free and yeah. Yeah, I don't know, and there's some argument. Using the splitting, one has to prove that law 1 vanishes. That is the homological proof of this. There is no canonical choice of the Saman. No, the Saman will be it's inside itself as a that's all. Yeah, I don't know what like what they call operator. No, I don't think there's no spatial. No, actually, the proof uses the Reynolds operator. That's what I remember. I mean, when the proof that tau 1 would be 0 uses the Reynolds operator. Yeah, that's what I. Yeah, not that's why it is works specifically the non-modular case, not just with the assumption that SG splits out of this.
So we know for P groups as G is F-level.
Yeah, which fit splits.
If it's
Correct. Yeah, it is Gordon's time. So that's all part of Grover's, in which he translates from the original formulation and talks about direct Saman property. He proves that if it splits, it is Gordon's time, and therefore whatever singularity, it is the best. Yeah, you cannot do it.
you say anything about the filtration?
No, so that one has to write down the basis.
Very canonical.
No, it's not. Probably not. I mean, no, because it's not very. And the only thing that we're using is that G itself, because it's a P group, can be diagonalized. I mean, they are all diagonal. I mean, sorry, not like triangular. Yeah. And so, yeah, so it's not a non-equal. Huh? Yeah, but I don't think the filtration is particularly canonical. Yeah. So it depends on the choice of basis with respect to which it was written into triangular form. And this will, the same thing will work in respect, I mean, in every such choice. So I think there is no canonical.
Any other question? If not, let us thank you. Take for tea now for 15 minutes.
Yeah, yeah. No, it's not. But it's a, the rules I know. Yeah, they all. Yes, yes. I know. So you don't get that is sufficient. That's the case. What you can do on application to mechanics. So the one direction established. But is it focus? Using what it. The other one requires.
But if purity in plus Rhodesian doesn't imply a filter.
No. It's not F F pure. It is splits, not F. It splits. It splits out of S, not out of. Sorry. So if F equals is positive. Huh?
There is no filter.
Okay, and it's wrong. It's wrong here.
But it has it means a positive.
Yeah. If it splits out of direct amount of protein that is positive, positive. That's it.
But I thought in Rhodesian we had
It's positive because S is positive.
we also I mean in theory it's not.
No. It is not the absolute statement. Yeah. Yes. It's sort of a statement positive. And then it's called special form. I'm not proceeding any further on the F that that's what it is.
It's in S.
It's
It has
S
got
positive.
positive. I thought it's
No. Then it's going to the from the filter. You cannot proceed it further on this.
I just put that first link. Hold on. I'm going to
file there, we have to open it. It is on the desktop.
Master internet.
No, not
Last.
I mean, maybe not all of
Yeah.
Okay, due to some connection problems, we have to change the schedule. So this talk will be delivered by Professor Dilip Patil from IIT Bangalore, and he will speak on trace forms and rational forms. Shall I start? Yeah. All right, so my lecture is very simple. Actually, it's more of a expository in nature. Some questions are there, and will be use of so-called trace forms to count the number of rational forms. So this is an expository work with Professor Jugal Verma, that we were trying to understand theorem by a computer scientist. It is called a TRS. I mean, we will come to it. And also, there are a lot of thoughts are
influenced by my association with Professor Storch. All right, so let's start. So
Yes, what? This is
go up and down.
up and down. Consistent. Plus this. What we. Okay.
So how do we do that? Space?
Down, right. Down. Back.
Right. Head on.
Yes. Yes.
All right, so I will keep the field as general as possible, but whenever I need to assume some more things, I will say that. So let's take the field, and for the sake of completeness, I am recalling some standard definitions which are well known. So, for example, the points in K, I will identify the algebra homomorphism from a polynomial ring in n variables to the field K. By the point when the algebra homomorphism defined by all variables xi is going to ai. And similarly with the K spectrum, that means the maximal ideals defined by the point. That is, they are generated by x1 minus a1 and so on. And that have a special property that when I go not maximal ideal to the polynomial ring, I get the residue field is the K. So this is the identification, and so these points are identified with maximal ideals whose residue fields are K, and they are called the K spectrum. One possibility of explanation is also the word spectrum actually originated from the spectrum of a linear operator and that will match with this if you think correct. So this is the K spectrum. And the maximal spectrum is the set of all maximal ideals, and the prime spectrum is the prime ideal. So the K spectrum also one calls them as a rational point because they have the points in K power n and the coordinates are in K. So this will also one can also do it for arbitrary K algebra. If you have a K algebra, then homomorphism from A to K, and the maximal ideals whose residue fields are K. We can identify with this identification. Psi going to the kernel of psi. And this is mapping of bijective. And therefore, we can make the following definition. For a K algebra A of finite type, this subset is a subset of the maximal spectrum whose residue fields are K. That I keep calling it the K spectrum. Now, what is it? All right. Now, to match our standard algebraic geometry notation of the classical notation, if I have an ideal A in a polynomial ring, then decay of the ideal A, all those points where all polynomials in that ideal vanish. And this is usually called the variety defined by ideal A in the classical sense. But these are actually the points. They are rational points. And that can identify this algebra homomorphism from A to K and also to this rational point, K spectrum. For example, suppose C is algebraically C is the complex number that we know it is algebraically closed, and in that case, what would say that all maximal ideals are the points, and they are identified the complex. Whereas for real numbers, there are many, very less number of rational points. Because you can see there are many maximum ideals which are not which don't correspond to the points. For example, square plus 1 and remaining variable, not there in C, not R. All right, now the question is, so this is the general question. The general question is, suppose I have given an arbitrary field and K is a finite type algebra of K, then one looks for a criterion which guarantees that A has a K rational. That means we want to find a maximal ideal whose residual field is given. And as you saw, it's not always the case. So we want to find the criterion, want to check somehow that the field, the algebra has a rational. So obviously for this problem, we can assume that it is a finite algebra because you can further go mod and then assume it is a finite dimensional as a vector space over K. And in this case, what is the K? Anyway, K spectrum is contained in maximum spectrum is contained in the spectrum, and all these are finite sets. And again, Duchendar's tells the equality holds if and only if actually K is algebraically closed. So for algebraically closed, we always have lots of rational points. So only the when field go down, go modulo some ideal. But suppose show the wrong ideal, there are no rational points. No. If you have a finite type algebra and you want to make it finite.
No, but go modulo some ideal.
Yes.
Maybe show some wrong ideal and then
No, choose a proper ideal. No, you see, for example, you can choose the system of parameters.
no parameters here rational.
Right? So you can go mod.
You are explaining why we can always people from finite and that's my
Yes. So you can go modulo some, let's say, power of a maximal ideal.
but that maximal ideal cannot have.
Yes. So you can go modulo or maybe the polynomials, some suitable polynomial so that it becomes a finite ideal.
But then it is out on some other case.
Yes. Or maybe you look at it like that. Even if I answer for finite type, then I am not really worried about how to read it.
This is itself an interesting thing.
Yes. Itself is interesting. All right. The next page. Now, when one says the criterion, that means what conditions on what? Conditions on a field that obviously also we realize that we need to put a condition on a field. For example, suppose the field is Q or a finite field, then this question will become much more difficult because we know from the number theory experience that finding a rational point was a tough job and so on. So this field is obviously I don't know what to do in this. All right, so therefore I am going to assume the field is a real close. And real close means essentially it's like real number. That means if the sum of squares, so then each one of them is. And here no non-trivial real extension. Then such a field is called as a real. But all these proofs which are presented today, they will work exactly similar way as will work for real. So I will assume most of the time that the field is real, R. And the most important thing which we use in this is the algebraic closure is of degree 2. And in fact, the algebraic closure you can find out by adding square root of -1. and the Galois group is Z mod.
A has no non-real expression.
A real field means if the sum of square is 0, they reach AIS. That is only the real. And a real close means there is no non-trivial extension, which is again real. All right, so these are very standard results when one goes with probably in the first course on Galois theory or algebra. All right. So therefore, I said we may assume, I will assume now R K is real number and the algebraic closure we know is C. And now we come to this question because we saw a paper published in computational algebra. Somehow this was interesting to computer scientists. And they were checking, they were giving proof. Actually, they were doing more. They wanted to know how do you count the points? How do you count how many points are there? That was the intention. And actually, we wanted to understand our way and what basic commutative algebra is, what linear algebra is. So that is how we started reading at that paper, and then we tried to write in our style, which will use basic commutative algebra. And that is how this article is published in this was a volume dedicated to David Eisenberg's 75 got recently got published in 2020. So this was okay. Now some more list. So actually this question goes back very long back. For example, Sturm, Jacobi, Hermite, Sylvester, Hurwitz, they proved fundamental results for counting zeros when the number of variables were not more, they were just 1 or 2. And probably one would have learned theorems like Jacobi or Sturm on the how to count the number of real zeros of a real polynomial. And even Descartes, but those answers were modulo 2 they were doing. They were not counting actually, they were only the parity was. Now, Hermite was the first. I've seen the paper of Hermite in around 1852. Actually, he was the first to count the number of zeros by using the forms. And those are called Hermitian forms. So Hermite introduced Hermitian forms for this problem. And similar, more general techniques are also used in the book of that Peterson, Roy, Spinglass, which I will sketch the proof. And you see the proof is not very difficult, it is only very standard commutative algebra and good amount of linear, which is also very interesting. So, now come the symmetric bilinear forms. So everybody knows what a symmetric bilinear form on a finite dimensional vector space. And I will identify C, the characteristic is not true, with associated quadratic forms. This is very standard, so I will, and probably I will not much about the quadratic forms, but as you know, quadratic forms is also very interesting. Okay, what is well known? This will learn this decomposition theorem in maybe BSc linear algebra or MSc linear algebra, that you can always find a free orthogonal basis of a vector space. That means you can find a basis of a vector space over A such that for the Grams matrix, and then it's a diagonal matrix because orthogonality means E of Vi which is 0 or I not equal. And now because the field is ordered, then you can collect and rearrange it so that the AIs are positive and BIs are negative and few of them zeros. And these integers P and Q are very important. So that is the Sylvester's law of inertia, which says that the natural number P and Q, which we got it by choosing a P orthogonal basis, those doesn't depend on the basis. In fact, we can describe it nicely that P is the maximum number of dimension of a subspace where phi restricted to that subspace is positive. And positive definite means for phi xx is positive for all x. And similarly, Q is the maximum dimension so that phi restricted to that subspace is negative. Then, so P plus Q is a rank. That is obvious because it's a diagonal matrix and Q it is non-zero, remaining as zero. So P plus Q is a rank. And P minus Q is the signature, it's called the signature, and the pair P is called the type. And we denote rank, signature, type by rank C, sign P, type C. And then the idea is to count the number of rational points by using these invariants. Now, this criterion is very important to do its criterion. And this is one of the key results that will be used for counting. So if V is a finite dimensional vector space, if basis U1 to Un, and if the principal minors of the grounds matrix they are non-zero, then the type is n minus 2, comma q, where q denotes the number of sign changes sequence of principal minors. That is how one counts the type and therefore the signature. All right. Now, this is also important. So first of all, when in general, of course, R by star, then we have no need to explain more because whenever I talk about open property, etc., then I take the standard topology on dimensional L vector. That is the standard field vector. And if K is real, in that case, K also has a topology by using no intervals. Intervals make sense. So that interval topology that is similar to the ingredient topology. So that is the topology when one talks about openness, closeness. But it will also be open in density topology. Sorry? It will also be open in density. But anyway, I am not using that for this kind of thing. All right. So, this lemma will tell you why it is called an open property. This type being a type PQ is an open property. It will follow immediately from this lemma. So what we have to prove? We have to prove that if at a point the type is PQ, then one want to find an open interval around that so that the type is constant. All right, now here little bit this funny notation I have to use because this is for the open interval. So I just because not to get confused with the type PQ, one might think that is also an interval. So for that reason. So suppose I have a polynomials. N squared polynomial, so that I want to get a symmetric matrix. And at a point, suppose if I have this matrix, this normal matrix in MNK, so this suppose that defines a non-degenerate symmetry by non-degenerate means the rank is full. Then I can find a epsilon positive such that types of all the grounds matrices GT. This T is integer interval, open interval, the same. then that would mean it is an open field. And the proof is very simple. So, as I said, main ingredients are Sylvester's law of inertia and Hurwitz. So, by use Sylvester's law to make a linear change of coordinates so that the ground matrix at S looks like this diagonal matrix. The rank is full, therefore there are no zeros there. K's are positive, K's are negative, P plus Q is N. All right. Now take any T. Look at these principal minors. They are the functions of T. And they are polynomial functions of T. Therefore, these functions are continuous. So T going to DMT are polynomial functions, and therefore they are continuous functions. And therefore we can find absolute positive such that the DM never vanishes in that interval. And that you can do it for all because there are only finitely many functions. You can choose epsilon so that they are all non-zero there. But now you know Hurwitz criterion, they have the same size there. They have the same size.
So it's not that slow.
Sorry?
Not that slow. And typology is right. You can't use that.
No topology.
No. This is not okay with directly topology. They are asking
Okay.
because positive is not something directly.
Yes. So the all right. Remark the above lemma. See, there was an assumption in this lemma that it's a non-degenerate. So the non-degenerate. I started with non-degenerate at S. So if it is not non-degenerate, then one has to be a little bit more careful. Then you cannot conclude that, but what you can conclude is to take a small neighborhood around that S, then the type will have these inequalities. P prime may be bigger and Q prime may be bigger. So because they may have zeros. So that not that is just all right. Now this theorem is very important. So that says rigidity theorem. So for wrote there for quadratic form, but this is symmetry. So and I have written it for. Sometimes in these notes they are very self-contained notes, so I wanted to write for all the real proofs so that I don't make any mistake. So you have a now rational function on a line connected subset U in K power n. Line connected means if you have 2 points there, then the line connecting them completely line in. So U is a line connected subset, and this is a symmetric matrix, and determinant is non-zero, that it's a non-degenerate for all T in U. Then all these matrices have the same type PQ. And equivalently, the same signal. Equivalently, because they are non-degenerate from P minus Q, you can also get Q because the rank is fixed. All right, now this is also similar proof. So it is enough to prove that the signature on a line segment is constant because we know just now we proved in a lemma that being of type PQ is an open property. So if I prove it 2 points, I wanted to do the types are equal. Yes.
Like real numbers, is the interval connected in all your real fields?
Yes. No, that is an assumption. No, what is your question?
My question is if I have a real field, what is that? And if I take the fourth interval 0 on,
Yes.
then connected in this super, yes. Like
Because it is everything is same. Say interval. I mean, order is there on the field. No. See real.
but you use kind of completeness in order to connect it. So assume that it is
intermediate value properties.
Intermediate value
for
properties
real
too.
space. Intermediate value properties for real space.
In fact, the intermediate value will characterize that field. So the ordered field where intermediate value theorem is true will be real close. So these are very standard results one can find in it, like Jacobson.
Weakness is recorded is asking when you need to be ordered. Yeah, so, but the order of weakness is not visible from that sum.
No, but there are many various characterization of these real close fields. No.
Okay.
It is characteristic 0 is a consequence that
I need to read.
the base reference is Jacobson and preferably
Volume 1 Jacob.
no, I would say volume 3 lectures on abstract algebra Jacobson. The old one. That is my favorite because in the new basic algebra books some topics are used. All right, so it's enough to prove that the line segment, the signature is constant on the each line segment. But for this, to parameterize the line by usual standard 0, 1 parameter. So usual standard one what you write. You have a point x and y and we take the line value there. So that's one big interval. And again the same argument. Now you see, assume that they are rational functions. So I clear the denominator. Because these rational functions are defined. So Gj, the denominator will not vanish on this interval. And therefore, you take the common denominator and now use the intermediate value theorem. It is true for real close fields. So you will get this after clearing before. So these are the symmetric matrices. They are the same type because the down one is non-zero, so can absorb the element non-zero by assumption, etc. So again, by Sylvester's law, the matrix, the symmetric matrix. Now I have taken that evaluated at 0. That is the diagonal matrix, and therefore, so you change the coordinates again so that it looks a diagonal matrix. In particular, the principal minors are non-zero polynomials for 0 to n, and this sequence is the one which gives the sign changes. That's at 0. But now you can partition that interval 0, 1 into several pieces so that the principal minors don't vanish there. So only we have to take care about the points where the partition points. So what is it? I will. All right, again use intermediate value theorem on subintervals so that the minors have the same sign, and hence the Lewis criteria, these matrices have the same type, and therefore the lemma will follow because the type is constant on this because of the openness of the lemma. All right, so in fact, this remark is also very important. It is not good, but it is interesting remark. In the class of order fields, the validity of the rigidity theorem will characterize actually the real close field.
Sorry, I got it. Suppose I take real numbers and I remove all transcendental numbers from
Or
transcendental numbers I remove 5,
that will not have
Will that be a real closed field?
Okay.
Will that be a real closed field? That real numbers minus constant is a field, right? So is it a real closed field? That field of the time. Right.
So that means you are taking the algebraic closure of 2 in R.
Exactly.
But what is the order?
That is your real number.
I think it is real. I mean, it is real.
So when one talks of intermediate value theorem, one has to interpret it as intermediate value for what kind of?
No. Okay. The polynomial function. Because they are only
So that's your intermediate is for, and that's all it is. For
Yeah.
polynomial.
because see we will I have never considered other than the polynomial function.
So it's okay.
All right. Now the trace forms and many more generalizations of the forms which looks like a trace form. So look back again. A is a finite algebra over a field. Then the classical tool of studying A is the trace form. Yeah, the more further remark we will also show that how what does this about the structure of that. So which is a symmetric bilinear form, and what is that? See the pair F comma G goes to trace of F. And when I say trace of an element in algebra, you take the left multiplication by that element, and that's a linear map, and you take the trace of that matrix corresponding to that. You take the trace of that, and as you have seen in standard linear algebra code, it doesn't depend on the basic. So that is a trace form. It is a bilinear form. All right. Now, because the orthogonal basis exists with respect to any form, in particular the trace form, so that means you can decompose that A into R components, an orthogonal decomposition. So when I say R component, R A into the local component, that means you have a finite algebra, so it is zero-dimensional ring, Noetherian ring, and then where the maximal ideal and prime ideal are same, they are finitely many in number. So you to look at the component, take the localization, and they are acting in local thing, and those are the components. Those are those AIs. This decomposition in particular is what the Chinese inventors the decomposition. And therefore the trace form is split into orthogonal components where each, so this one, the trace form on given and so on.
If we show page 20, the previous page,
Sorry,
we show the last page.
last page.
Page 20. I don't know. Previous time.
This one. All right. Now, what is the degeneration space? That means where it becomes zero. So now note here that when I write then suffix A, that's the Josephson radical, then suffix A is a Neal radical, so all maximal radicals, all prime ideals, but you are in a zero-dimensional case, therefore prime ideals and maximal ideals are same and both radicals coincide. And obviously, the decoder will have range 0, so therefore this radical is contained in the degeneration space. Moreover, the equality holds if and only if all the residue fields of A are separable over T. See, trace and separability they are very closely connected. So therefore, all residue fields are separable over K if and only if the reduced ring A by going for the Lie radical, they are all separable algebras. And separable algebra means every element is separable. That means the minimal polynomial of an element and the derivative of that, they are co-prime ones. All right, so those are separable ones, separable. And so far, we have not used much about the field. In particular, trace form is non-degenerate if and only if A is a separable algebra, because the degeneration space has to go. Therefore, that star above that will tell you rank of a trace form with the dimension of vector space dimension of A by the Jacobson radical, which we know it is equal to the sum of the residue field. If A rate is a separable algebra, where A has the residue field of A and the maximum vector is 1 pair. Moreover, now, so far it was going on for arbitrary field. Moreover, if K is an ordered field, then the type of this, the trace form will decompose. So type is the sum of the types. And the signature is sum of the signature. So that follows because of the decomposition. The decomposition. The decomposition is not the type here because there is the orthogonal basis for each and then similarly for the type. So we have this order. So type can decompose, sign, signature, and signature. Now, we prove the very important classical criterion for existence of Ration points. Stop. And it says that if you have a finite algebra over a real closed field K, then the number of Ration points is the signature of the trace. In particular, if K is the residue field of A, then because if K is a residue field, that means the number of is non-zero. All right, now you get trace K over K. Obviously, this sign is 1, and therefore by the double star formula, it's enough to show that the signature of a trace form, if your field extension is non-trivial, then it is 0. Because as long as the component, the residue fields are K, those are non-zero, and the remaining part, two are zeros, then we are done. All right. To prove this, I will consider for arbitrary element x in L non-zero, you consider a new bilinear form. New bilinear form is Fg going to x times Fg, trace of it. All right, all these forms are non-degenerate because L over K is separable. And we are assuming L is a non-trivial field extension, so the dimension is at least 2 and therefore structure space is line connected. And hence, by rigidity theorem, the signature is constant on the punctured space, L cross. In particular, the signature, the trace form, is signature of phi suffix 1. X is 1, then it is the trace form, x is minus 1, it is the minus 1. And signature of the minus trace form, minus sign will come on. So therefore we got, what did we get? Signature of the trace form of L over K equal to minus signature of the trace form of L over K. So therefore this signature has to be 0. And that's what we wanted. Can I go on? Now just write down a small example. So for example, trace of Q over R respect to R is 1 comma I. How does one compute it? So this is the Grams matrix is trace 1, trace I, trace I, trace I squared. No? Think of inner world, no? 1, 1, 1 I1, and I. So those are, you have to compute this. So trace of 1 means trace 1 will correspond to the identity value. So that we get trace of I, trace of lambda suffix I, and lambda suffix I, that means multiplication by I. The matrix corresponding to the base is 1 comma I is I will go to 1 will go to I, so 0 1, I will go to sorry, I squared. Minus 1. Yeah. Should be minus 1. So anyway, trace it. So trace of 1 is 2, trace of I is this 0, and therefore this matrix is 2 minus 2 0 0. That's what happens. So trace 0. The type anyway, type is 1 positive, 1 negative. So type is 1 1, signature is. And R spectrum of C over R is also 0. There is no real point. There is only one point, and that is a complex point. So R spectrum is empty. Corollary. Here is a finite R algebra. Then the trace is positive definite if and only if A is separable. And the algebra is separable, just now I said no. The isomorphic go generated by one element x, which is R polynomial x modulo the minimal polynomial of that x. And that minimal is x, such an x is called primitive. Just we have to be little careful because we are not in a field case, but we are in a finite algebra. And you will see the difference. Later on I will tell something. So in general, look at the comment. In general, a finite separable algebra or an infinite field always have a primitive element, but you need to assume the field is infinite. That is because you look at this example. Suppose you take k power n. That is the finite algebra over k. But it may not have a primitive element. Because no, that primitive element means you need an element where the minimal polynomial of that element should have degree n. But that cannot happen. For example, if you take a finite field, only finitely the component may be equal. If n is large, the components, if n is the cardinality of the field is smaller than n, then every tuple will have at least 2 equal points. And then in that case, the minimal polynomial will not be of degree n, it will be smaller. This is a simple exercise. So not all finite algebras have primitive element. Need or some other assumption. All right. So what is the statement of the corollary? If it is positive definite, that is equivalent to saying A is separable over K and it splits over R. Separable over R and splits over R. Splits means A is a product of algebras. So further notation more clear. Now corollary, next one. If F is a single polynomial, monic, then all zeros of F in C, they belong to R and are simple. That is if and only the trace form of the algebra mod F, the algebra A and B. Trace form of this algebra is positive definite. Positive definite is so equivalent saying the type is n, 0. So the sign of the trace form is there. This positive definite equivalent to saying that the zeros are all real zeros and they are all simple. That is equivalent to the trace form is positive. That follows from the earlier. Very simple. Now, this is Hermit. Hermit exactly proved this. If you have a monic polynomial of degree n and A is Rx mod F, then the type of the trace form is R plus S, comma S. Sign is therefore R, which are the number of real points, and 2S is the number of non-real complexes.
So there is no algebra which is negative. There is no finite real algebra which is non-negative. Nothing.
All right. So the proof of this, we may assume that A is reduced because computing the signature and type, the only rank plays the role. And reduced name will get it by. All right. So we can assume it is reduced. The reduced means we can assume I don't have to do anything because I want to count the number of rows of points that the polynomial has. So each one has multiple factors, you can just discard them and look at the reduced part of the polynomial. And then it will look like, because it's a real polynomial, the decomposed, prime decomposed, saying the polynomial will be over R will look like this. There will be some real zeros and some polynomials which are of degree 2. That's the fundamental theorem of algebra. And these are the prime polynomial. Prime polynomial means irreducible and monic. So these are pairwise distinct prime polynomials of degree 2, and therefore pi j looks like this. You know the roots appear in pairs. Zj's are non-real complexes. And that's it. Now you know what is the type. You know what is star, R is star. So that was it. So this is very precise, but probably that time this language was not available. Because all right. So the next, now you see, if you have an algebra like this, Rx mod of polynomial F, Chinese remainder will tell you this algebra splits like this. Some real copies and some complex field copies, because the residual field either can be R or C, and few copies of C and few copies of R, and because it is reduced, This is precisely the Chinese remainder theorem. And then the trace form we split into orthogonal components, few times trace of R over R and few times trace of C over R. And how did we compute the type? The type is the sum, the types. And these types are 1, 1, 1, so many times. So each one of 1, 0, and each one of this 1, 1 that we saw. And therefore, the signature here is 0, the signature here is 1, so matches. All right, so next, actually, just a beginning, but I wanted to be sure with all the calculations, that's why I wrote all this. Now, I want to further generalize this term, because what I want to do is, which is not written here, but I wanted to use it for understanding polynomial maps, especially when the polynomial maps are suited, or more precisely when some element, some point in the image of the polynomial. So to understand this, one usually understands model. It's called a dualization, which is home K. When I write without ALG, that means it's just a K linear map. So home K, A comma K, there means that this means the elements are linear forms. This is a dual of A with respect to as a vector space. So this is also A model. We can do model structure from alpha is a linear form on A, and linear form here from define it by F going to alpha H. This is the natural structure of A module structure on the linear forms one. This is called a dualization. And commutative algebra, they so dualizing module is very much when we study Ration. All right. So this important thing to note is this E can be embedded as a K linear map. Embedding K linear, not so E can be embedded in the space of symmetric bilinear forms only. How? Take any linear form, and I want to define a symmetric linear form by using this linear form. So you send F comma G to alpha H. And because we are considering only the commutative case, it is indeed symmetric, and it is also bilinear. And now I am going to replace the trace by this. Now I have so many of them. Many linear forms, and also therefore I have many symmetric bilinear forms, and we have whole family of symmetric bilinear. Okay. So again, now one wants to understand a degeneration space. So degeneration space of E alpha means what? That means where the elements are perpendicular. That means Phi alpha evaluated on the pair if GF is 0 for all G for F. So you collect all those F, and that is obviously contained in the kernel of alpha. Kernel of alpha is a subspace. Alpha is linear form. So kernel of alpha is actually a hyperplane. All right. So for each alpha in E, and this is contained in the kernel, so it can go more kernel, and then you get the linear form on A bar. And obviously the rank will not change of rank of E alpha and rank of E alpha bar are same because you have just gone mod the kernel. So therefore the new bilinear form E alpha bar is non-degenerate on A bar. Moreover, if the ordered field you need to talk and you want to talk a type and sign, then only you need to compare the, so you need an order. So then the type Phi alpha and type phi bar alpha, and similarly signature Phi alpha and their alpha bar is there because they've just gone modular. Now the lemma says if you have a linear form on A, then phi alpha is non-degenerate. So non-degenerate condition I wrote. That means for all f in non-zero f times alpha never becomes. That is a non-degeneracy condition. That means, what does this mean? This means A alpha is actually free submodule of A over E. It's a submodule because A alpha is contained there and it is generated by that alpha, therefore it is a free submodule of the module of linear forms. Moreover, the dimension, A vector space dimension of the equalizing module and A are same. Therefore, they have to be equal. Because one containment is there, the free and there the dimensions are same, therefore the equality will happen. So therefore, actually what it proves is that dualizing module is a free module of rank 1. And not only that, it also gives you a basis. That alpha is a basis. So if you want to find a basis of this module of linear forms, then you have to test only the symmetric bilinear form corresponding to that linear form is non-degenerate. The checking gets converted to linear algebra where it and it check or we have more experience taking linear algebra because just have to take a basis and find out determinant. All right, so what did you say? So, by the way, also see the literature, finite algebra is called as commutative algebra. If there is a linear form, so that C alpha is non-degenerate. This is equivalent to saying that the module of linear forms on A is a free module of rank 1. Those are the problems. All right, for example, if you take any linear form and go on to degeneration space, because that alpha bar will become non-degenerate. All right, now we can generalize that theorem of course. But this is not now if and only fit, but it gives a criterion to assert that in the KRS. Not criterion, but it only gives you a condition. So if alpha is a linear form and a finite algebra, how long? 1 minute. So how much I have time? 1 minute. 1 minute I cannot finish. All right. So let me finish as earlier. So let us do this. So I have given a linear form so that the signature is non-zero and I want to do that as a Ration. So replace that linear form by alpha bar and assume that phi alpha is non-degenerate. And now consider the family of this. Now you multiply this alpha by f. The model, a model, and f varying states. And this is a unit number. So suppose it has no k-rational form. Then what happens? Then the residue field at n cannot be for all maximum. That means codimension of that maximum ideal, when I say codimension as a vector space. That means by definition, dimension of A by M. And hence, see now here, okay. All these guys have codimension. And this is from A we have removed codimension. So this is the finite algebra. So think of Rn, and then we have removed finitely meaning 2 codimensional systems. So that will be incorrect. See, imagine C cross, then you have a line. Dimension is more. So that is line connected. You can always C cross, you can it's line connected always, because given two complex numbers, you can find a line joining them completely. Line means now maybe what is it? Not one line, but several pieces of. But then the rigidity theorem will tell you that all these forms wherein have the same signature, because this is the U I am using from that theorem, which is line connected, and therefore signature of alpha in particular for all f it is same signature. So I will take f equal to 1 and f equal to minus. So signature of alpha and signature of minus alpha are same, but this is minus of this, and therefore the similar idea as the Stolz's theorem. And therefore signature is 0, but that is a contradiction. Well, our assumption was now maybe the last corollary. Okay, I will not trivial extension finite extension of a real closed field is only one anyway, because the theorem says the famous theorem of Euler-Lagrange is that there is only one non-trivial extension of a real closed field, namely the algebraic, and that is of degree 2 and the identity form. So actually, now the actually interesting part will start, but I don't have time. All right, so I have to stop. Any question? Before this. One more. You are saying the one versus not no, only one way. I don't know the answer. Only one. But I am asking for an example. So it's the other way. See, this you are asking which form will give you signature 0, right? But the earlier part will also tell you the answer. That means if you take a linear form which is filled by one element, just one element in the algebra, that's enough. So that goes the degeneration space and then okay. All right. Now can I see? Any more questions?
So do these methods give some understanding of division algebras?
No, I did it for division algebras are non-commutative, so I will not have it. But this will give also some.
So are there some significant theorems? Because over here there are only 3 or 4 division algebras, right? On a real sheets also same theorem.
Which theorem?
There are only C whatever.
No, that's a no. Real prose. Real prose means therefore the only extension, non-trivial extension.
That is commutative. I'm also of division algebras.
I have the other one.
What are you counting for? What do you mean by?
No, he is asking what do you do? Whether does it help you to count the division algebra? I don't know. And because
None of these methods work. Is there
But what-
Artesian ring a product of working local? That is crucially used.
Right.
what I wanted to do was I wanted to study polynomial map from same polynomial ring, number of variables are same, polynomial map. So we will give you a map from k power n to k power n. And suppose I have given a point y to k power n. how can I conclude it is coming from the image? That means the fiber algebra should be have a k-rational point.
Yeah.
And then this method, yes. Because see, this method tell you if you have a finite algebra over a field, whether is there a rational point.
Let's thank the speaker again. We'll break for 10 minutes. Oh, there's no,
No, you
there's
can
no
break,
question.
but then what?
There's no question.
खत्म हो गया.
So tomorrow we have a conference dinner. Sorry, today. The 7:30.
Same place?
Yeah, and the bus will leave at 9 o'clock. The same place. Yeah.
I go in the morning with,
Yeah.